Hi, hey everyone. Sorry for the delay. I didn't realize that this didn't take lightning over here, so yeah, let's do a little bit jank way of sharing this. But oh, hey everyone. Sorry that you guys have a midterm on your last day of class, but it shouldn't be too bad. The topics we'll be covering are potential flow theory, um, Buckingham Pi, and then Navier Stokes, right? And then doing something else here. My another guy from PTF will be coming to help teach the practice problems later, but for now we'll go over the same thing as last time: content review in the beginning, and then like one or two practice problems. And then we might end early, so then any questions afterwards, you guys can just ask me. Yeah, let me do one thing actually. It's fine. Okay. So let's first start with potential flow theory. So the main, or like the first thing, is that we have a few like equations that just describe different characteristics of flow. Let's just start off with something called vorticity. Vorticity, I definitely spelled it wrong. Vorticity. Yeah. And then the formula for this thing is actually vorticity is technically just this, okay? But this is just equal to half of cross B. And does everyone know what the curl is? It's from probably Math 53. In two dimensions, which is probably again, one thing about potential flow is that it's pretty much only in two dimensions, so you won't have to worry about like 3D flow or like other like the third dimension. So for 2D flow, your vorticity would basically be dv dx minus du dy. Or like I guess half of this, right? Times half. But so this is your vorticity. Another thing that is covered in your note or in your chapter is something called rate of shear strain, which is dx plus du y. And then there's also something called volumetric expansion rate, which is that's equal to du dx plus dv dy. Okay, yeah. So these are the three kind of starting, or like the three kind of equations that come up in this section. I guess one thing, does anyone know, suppose if your flow is incompressible, let's say, what would your volumetric expansion rate be equal to? 0? Yeah. So and if your vorticity was equal to 0, what does that tell you about your flow? Irrotational? Yeah. So then also W equals 0 means irrotational. Okay, yeah. Yeah. Direction. It should be counterclockwise by convention. Oh, sorry. This is in the K direction. Yeah, that should be in the K direction. Yep. And K is in technically the into the page or three-dimensional direction, but for the purposes, like, I mean, you wouldn't really need to worry about the direction, but yes, it is in the K direction. Okay. And then, okay, so then how does this relate to the kind of things that get covered in this chapter. So the first thing that we're going to talk about is the stream function. So the stream function only exists if this incompressible if this equation is true here, then we can say that this implies existence of stream function. And I won't, unless someone wants me to, I won't go into like why that is. But if you can prove something is incompressible based on that formula, then you can do your like integration, find a stream function after that. So call that psi, right? And then the formula, the basic formula for your stream function is u is equal to d psi dy, and v is equal to negative d psi dx. Cool. And then in the same way that you learned in like multivar, if you you can just integrate this to find your stream function. And then there's also polar and like cylindrical coordinates, but that'll obviously be given on your cheat sheet if you need it, or it'll be given just in the problem how you're supposed to be working with those. So for now, you can just keep these as like the basic ones. And then another thing that we see about these, now that we have the stream function, one thing we can say is that the psi term, the value of psi is constant along a streamline. So if you have like, so what does this mean? This means that suppose you have like a stream function, or like you have like a field, or they've given you like an image, and then there's like a stream function all over like this domain. Basically, wherever the values of the streamline or the stream function are constant, that basically dictates your streamline. So if we had like, I don't know, something that looked like this, some flow that looked like that, right? At every single, this is one value, another value, and then it keeps going. So for along a streamline, you'll have a constant stream function. Okay, and then another thing that comes out of this is that the difference between your values is equal to, this is the volume rate of flow. So if you had, I think the book does it like this. If you had two like streamlines like this one is at psi 1 and this one is at psi 2. If you were to basically try to find the flow that goes between this, so how would that work? The flow between these two is basically just given by the difference of these two values. So that's like the flow between. Yeah. I can pull up like the equation for why that works. Give me a second. Okay, yeah. So basically it's actually, it's volume between it. Sorry. It's like this. Yeah, the volume. Yeah. So you have a flow through here. So basically how it works is that if you draw like a line that goes through here, or I'll draw it down here. Okay, so basically you have 1, 2, have a line between it. This is your dq. This is the flow between it. You have u coming in like this, and you have a negative v coming in like this, and then this is dy and this is dx. So then in general, the flow rate that's going through that like little squiggly line is going to be equal to u dy, because it's same how flow rate is velocity times an area. Right now it's in 2D, so it's just like a velocity through like one line segment. So you get u dy plus minus v dx. And then if you're to substitute your equations from here, you would basically say that dq is equal to d psi dy plus d psi dx, and then that by definition is equal to d psi. And then if you were to, so now this is over a differential like element. If you were to just integrate this over, so then q is just going to equal to q2 minus q1. Yeah. So then if you just by definition, if you just derive the equation for a volumetric flow and you substitute in your function for psi, it'll just come out to the fact that the difference between the two streamline values is just equal to the flow between them.
Question.
Yeah.
Potential will always be positive, right?
I guess it doesn't matter. I'm not entirely sure if that's like an absolute statement, but the exact value of the stream. Oh, sorry. What happened? The exact value of the share again. The exact value of the stream function doesn't matter. What matters is the relative distance between them, because even if it's negative, there'll be the same like difference between the two values. So even when you integrate to find your stream function, typically if you've seen like the homework solutions, they'll like just take the constant out. If there's just like a numerical constant, because the actual value of your stream function doesn't matter. Yeah.
Wait, sorry, I'm a little confused. So you said that the value doesn't matter, but
the difference between two values matters.
Yeah. Which is always going to be positive.
Yeah. Yeah, I mean.
Yeah, negative distance. So in the equation, it's negative v, so like in this case.
Now I'm just seeing technically if you just look the integral here, it'll swap. Or those, no, that would be fine. Will it be negative? I mean, it could, like the actual value, I mean, you can set whatever constant you want into that. If you set like minus 1,000 to it, like it doesn't functionally change the u or the v. So in that sense, yeah, it could be. Yeah, it's volume per second, right? Yeah, the volume rate of flow. Yeah, it's volume per second. Yeah. But keep in mind that this isn't 2D, so it is volume flow like per like unit, because you're not looking at their dimension. Yeah. So to get like actual like in the right units to get volume, you'd have to like add like one length dimension or like multiply by one length. Oh. Because this is u times like a line, which is in one dimension, right? Normally to get volume, you do velocity times an area to get like actual volume.
So this is the area.
So this is in 2D. In 2D, we don't look at area, right? Or if you're looking at flow past, you don't look at flow through an area, because that doesn't work in 2D. You look at flow through a line. So it's just one length dimension down than like a normal like flow rate dimension.
So it's
But in three, the thing about potential flow theory is that it only works in 2D. You can't have this in the same stuff in 3D. So don't worry about that. And then okay, yeah. So the next part is now that we've found the existence of this stream function, we can also now there's also a different function called the potential, the flow potential, right? So how does anyone know under what conditions the flow potential exists about the flow? Yeah, what's up? Yeah, it has to be irrotational. So if we say here, if this is 0, this means that flow potential exists. And then the way you would do that is you would, again, same thing, go back here, go do this equation. If it comes out to 0, then you can say that the flow potential exists. Yeah, and then the flow potential is a lot simpler in terms of its like relations. You get phi dx and v is equal to d phi dy. Yeah. So any questions on this so far of how you would go about like either proving the existence of a potential flow or like any of the differential like quantities you talked about? What's up?
So is it like we first find the phi function and then if the potential flow exists?
So if you're given the phi function, then that means by definition it exists. It's the only time you'd have to prove it is when you're given the velocities, and then you don't know if you could integrate upwards to find the phi function. So if you're given phi, that means it exists. That's fine. Then you just take your normal derivatives and you're good.
But this phi is the same phi as.
No, this is different. This is for flow potential, and this other one is a psi. Where did I keep it? Yeah, here. This is a different. This is not equal to that. It's different. So a stream function exists if a flow is incompressible, and a velocity potential exists if a flow is irrotational as well as incompressible. Yeah. So I guess another thing that you can say is that this also relates to Bernoulli, because so if you're given the existence of a psi function or a stream function, that means that along that one constant value of your stream function, you can apply Bernoulli, right? Because that's along a straight line. So you can apply. Let's write that again. Apply Bernoulli's along streamline that we already know. But suppose you had suppose the flow is also irrotational. What you can say is that you can apply Bernoulli's anywhere in the flow. It does not have to necessarily be along a streamline. It can be like, again, let's look at the same. Suppose we had like a flow that went like this way. Like normally, or like it kind of like went around like this body or whatever. So normally you can only apply it between like points 1 and 2. But for some reason, if the flow was irrotational, in this case it would probably not be, but if for some reason that the flow is irrotational, then you can also apply it at point 3. Yeah. So then that restriction goes away. It does not have to be just along streamlines.
So consider the equation 1, 2, and.
Yeah, if it is irrotational. Yeah. Okay. Then now we can go over a few basic types of flows that you can describe using potential flow theory. So this will all, again, be given in your cheat sheet, but just to kind of briefly go over what they look like, I'll just like put them down here. So the first one, let's put like a line here. What do we have? Uniform flow. Uniform flow. So for this one, your potential function is equal to this. And your, I'll do this is equal to your psi function, and then your d psi dx equals d dy equals 0. So in this case, yeah, your u is just equal, so u is just equal to this capital U, and then v is equal to 0. And the way this looks like is that if you just had flow going just in one direction, that's uniform flow. Okay, and then there's also, if you look at your book, there is a case for angles, but that's just something that'll be on your cheat sheet. The next important one is something called sources and sinks. So a source is when you have fluid emanating from just one singular point, just emitting outward. So if we had a source slash sink. For this one, your phi is given in m over 2 pi natural log of r. And your stream function will be equal to m over 2 pi theta. So note that these are in polar coordinates, because for a source and a sink, since it's like radially symmetric, it's just easier to represent it like this. Obviously, you could use trig relations to like swap between the two if you ever needed to. We'll be doing a problem which will kind of go a little bit over that. But I guess, yeah, what's up? M is basically it's just a value that represents the strength of the flow. So the what? I don't. It's not the same as that, I think. Are you talking about this? No, that's for vortexes. It's conceptually also that's for the strength of a vortex, but it's not the same thing as this. M is for sources and sinks, and then that value that I don't even know what's called. Is that tau? Tau is for I don't think that's tau, like gamma or something. Anyways, whatever that is, that one is for the strength of a vortex. So we can take that out for now. Cool. Yeah. Yeah. So that's. Oh yeah, that's a good question. If the m greater than 0 is a source, and m less than 0 is a sink. Cool. And then the next one, as you mentioned, there's a vortex. So for the vortex, you have this function is k theta, and your psi is negative. Okay. What does it say what exactly that is? Oh, never mind. Sorry. It's a different one. Your psi is 2 pi theta, or your phi is 2 pi theta, and your psi is negative 2 pi ln r. Okay. And then in this case, a positive gamma value is a counterclockwise rotating vortex, and a negative one is a clockwise rotating vortex. So I believe this is CCW and less than 0. Again, and that represents the strength of the vortex. And notice that it is pretty similar to it's almost swapped as compared to the source and sink, where your natural log term is here it's in the phi, and it's on the psi over here, but it's very similar. Yeah, and then there are also things like a doublet, which will, but there's also things like a doublet which has like a different set of um, has like a different set of like equations, and that usually is used to depict like a, a circle in a flow, a doublet. So, but that's just another set of equations. But basically, so this is the basic equations. I guess one thing I'll also write here is associated trig functions. So you have x is equal to r cosine theta, and then y is equal to r sine theta. R squared is equal to x squared plus y squared, and then theta is equal to inverse tangent of y over x. Yeah. So, and I believe this also came up in some homework as well, like this at least this specific relation. So these are things to like remember, because in some cases you'll have a uniform flow, and if you can see here, uniform flow has it's yeah. So actually, where's that? Let me write that down. Okay, so yeah, and here for uniform flow, I'm sure your phi is equal to ux, and your size equal to uy. Okay, so in this case, you can see that these are in Cartesian xy coordinates, and these ones are in polar coordinates. So if you ever had to combine both those flows and like solve to take any derivatives or anything, you would have to put them all in the same coordinates and do that. But yeah. Okay. And then, yeah. What is the expression? Oh, this is these ones. Okay, so if you look here, you can just see that if you were to uh, if you're just to take this and just integrate it, you would get that, and the same thing for psi. If you were to integrate the psi function, you would get the same thing. Yeah. Yeah. So phi is the velocity potential. Um, yeah, phi is the velocity potential. Oh, I guess one good thing to note as well is that when you draw your potential lines and your streamlines, they're going to be orthogonal to each other, and that's actually another reason. Um, so you can see in the case of uniform flow, these are your streamlines. These go in the direction of your flow. So these are your psi, but these ones, other than red. These ones over here, these are your phi lines, and then they will always be perpendicular to each other. So if you ever if there's anything if you had to draw them, then if you already have if you have your potential or you have your stream function, if you just drew a bunch of curves perpendicular to those ones, you'd be able to find the other one. Yeah. That out of the way. Okay, and then the next thing that you learn is that you can combine some of these equations to get flows over different bodies, right? So one thing is that you have your flow over a half body, and then the equation for that, basically you take, so I guess superposition is the general topic, but so you can take psi is equal to 1 plus 2. Okay, I just say kind of confusing. Let's write, let's say for half body, you take for uniform flow and you add it to your source. So, and then this would just equal UR sine theta plus m over 2 pi theta. And you see here how, well, the actual stream function is, yeah.
So you're talking about the difference in sine and phi. So phi was the velocity potential.
Yeah. Psi is the stream function. So see in this case how this is actually uy as per like literally the previous page here. But they when you write it in terms of half body, since you're looking at polar coordinates now, you can write uy as ur sine theta. It's the same thing. Yeah.
You are saying that the R there is R component doesn't mean times R, right?
No, it is that is times r.
Oh.
That is times r. I guess we can just do this. That's easier. Yeah.
Oh.
Yeah. So then, in the same way, I mean, again, we don't write down every single thing from the book, but in the same way, this is a thing you can do. Suppose you're ever asked, like, okay, I want to have a vortex plus a I don't know, uniform flow, and that'll give you a rotating a rotating cylinder or something like that. It gives you, but there's just different ways you can combine all these stream functions to get to different things. Yeah. Okay. Yeah.
For superposition, is there a relative homework?
Yeah, I think homework 7 or 6. One of those had, you don't even know which one that was, which had like, I mean, it's just like you had to look at a half body or something, right? Okay. I can go double check. Yeah, it was on one of those. I know you guys had a problem like that. I'll go check that afterwards. Let me first do this. Yeah, but okay, cool. So that's the basics of flow potential. Again, remember the conditions under which you can use all of these things. So for a streamline, it has to be incompressible. First of all, everything's in 2D here. But for streamlines, it has to be incompressible. If you wanted to use a velocity potential, you need to prove that your flow is irrotational. Cool. Okay, so then I'll now go over Navier Stokes. That's honestly probably one of the more simpler ones because you have a bunch of complicated equations, but they'll all like kind of cancel out. You just got to cancel out as many terms as you can to get like a simplified, easy to solve thing. So let's go back to that. So I'll just write like one of the formulas for, let's go with this one. Okay, cool. This is pretty good, yeah. Rho du dt plus u du dx plus t du dy plus w dw dc equal to negative dp dx plus rho gx plus d squared u dx squared y squared. Okay, so this is just the u momentum of Navier Stokes. You can write the same thing for v and w, but let's just look at this a little bit. So what does this first part remind you guys of? Like a thing you learned? Something, it was definitely on your last midterm. What's up? What is it? He'll allow me. It's not continuity. It is, yeah. Yeah, that is the material derivative. So that's the material derivative on this side. And on the other side, you have a bunch of different terms. This accounts for pressure. This accounts for body forces. In this case, it's gravity. But you could, in the same way, in like the Reynolds transfer theorem, you add the like extra plus force term. If there's a different force, you can add a force term over here. But in most cases, it's going to be gravity. So you have this rho gx term. And then this accounts for viscosity. So that's all you really need to know about it. There's some key words that come up in a lot of problems that allow you to cancel out different things. If a problem is steady, Yeah, what's up? Yeah, what's up?
Slow down.
Oh, my bad. Again, this is all in the notes. But okay, if they describe in like a problem statement that the flow is steady, which one of these can you remove? Let's say you can just shout it out or raise your hand. So if they say a problem is steady, yeah, what's up? Yeah, good. Yeah, so if a problem is steady, any time dependence goes away. So all your du dt tier terms will all go away. Yeah, all your du dt terms all go away. Suppose they say a problem. I guess this depends on context, but let's say you have like flow that's like I think on one of your homeworks you had a flow that was along like a inclined plane, right? And then I don't know if they said that I don't know exactly what it said, but sometimes they'll say the flow is fully developed. Or if you have a flow just going through a pipe, let's just say you have a flow going through a pipe, and the flow is fully developed. What and let's say x is horizontal and like y is vertical. What term do you think could go away?
Dx.
Yeah, dx term. So I guess for a pipe it'll be cylindrical, but whatever the axial dz or that term. If the flow is fully developed, any dependence on your and in the direction of flow goes away. Obviously, if a flow is inviscid, this entire thing goes away. But then if it's inviscid, you probably will not be using Navier Stokes. You'll probably be, yeah, what's up? Inviscid means that there's no viscosity.
So the viscosity
If you were told that the flow is inviscid, but usually if the flow is inviscid and for the problems you're working on in this class, you just use potential flow theory because that's just an easier representation.
Oh, sorry. So when you say fully developed, is it the direction of the flow that goes somewhere, or is it developed?
Okay, I'm gonna write that down here. dt is equal to 0. Fully developed. The derivative will go away. So suppose again we had like I don't know, we had a flow that was going like this, and you had like a plate which is like driving this flow. If it's fully developed, that means x, y, your ddx term would go to 0. Oh, and again, this is just your du dx term would go to 0. Your pressure, if you have like flow going in this direction, your pressure there can still be a difference in pressure. So don't like arbitrarily set your dp dx term to 0, but your velocity will not be changing in the direction of your flow. So not every single ddx, just your velocity ones. But yeah, so that's mainly what you can say. Obviously, if it's 2D, which in most not, I mean, if you have cylindrical, it won't be. But if it's a 2D flow, then anything with W or anything with W or D dz goes to 0. So if you have a 2D flow, then if you go back here, then what? It's a better way to do this. Yeah. Then this term over here would go to 0. Yeah. And another thing that you'll have to use is, or also this term will also go to 0 in that case because there's a dz there. Another thing that you can use is that the continuity equation. So suppose you have du dx plus dv dy is equal to 0. And you know that your flow is fully developed. So you'll not have a du dx term let's write this, if fully developed. Then you can also say that your dv dy term is also this means that dv dy is equal to 0, right? Yeah. Okay, yeah, that's the other thing. If incompressible. But again, that's mainly what you're going to be working on in this class. But for this equation, it's generally going to be true. Or like if you're asked to find stuff for a flow, this is generally an equation that you can use. But in this case, you can say that your dv dy is 0, and that means that that means that v is constant, and then what you could say, and suppose okay, you can say here v is constant. Suppose somewhere in your flow you already know that v is 0. Then you can say that v is 0 for the entire flow, and then you are able to like cut out like this term. You're able to cut out like, actually that's the only term you can cut out, but you can cut out like that term as well. And then you can also cut out this term. This is technically a du dx term as well. But yeah, so if you're ever in a problem where you need to use Navier Stokes, the basic like strategy is to cancel out as many terms as you can. So look at the problem statement, see, okay, it's steady, cancel out a bunch of terms. It's fully developed, cancel out some terms. 2D, cancel out terms, and then it'll basically all like collapse into like probably one like easy to solve like differential equation. Yeah. What's up?
Can you go through the equation and just go through each of the scenarios?
Yeah. So for this one, if it's steady, you can remove that. I'm gonna be like erasing these like as I go, so I'm not confusing people who look at the notes later. If it's steady, you take out your du dt. If it's fully developed, you can take out your du dx. This du dx part of it will go to 0. If you go through this and you find where to go, if you go through this entire like process and you find that your vertical or your y velocity is 0, this term can also go to 0. If you're 2D, this term can go to 0. If they say there's no pressure gradient, for some reason they'll tell you that can go to 0. If they say no body forces, this can go to 0. If for some reason they say inviscid, this thing can all go to 0. Oh, I guess where'd I go? Yeah, if it's 2D again, this goes to 0. Yeah. So those are the main keywords. Yeah. Du over dy. So this term doesn't, in a lot of cases, it won't go to 0. To cancel out this term, if you can prove that v goes to 0, then that term goes away. But du dy is not a common thing to go to 0. Yeah. So that's pretty much all you really need of a Navier Stokes. We'll be doing a problem on that anyway, so you'll see it kind of being applied as we go along. But any questions? Yeah, what's up?
If it's fully developed, du squared and dx squared also at 0.
Oh, that's a good point. Yeah, I think so. Yeah, because if your du dx, if that derivative is 0, then your then yeah, you're right. This one would also go to 0 in that case. Yeah. So,
If we have fully developed, is that one of the terms of not 0?
If you have a fluid, I mean, depends on like what fluid. Because fluid it's in very specific scenarios. So suppose you have like horizontal pipe flow. Fully developed means you're only going to have flow in the axial direction. Or if you have like an inclined plane and it says fully developed, then it's only going to be, it's not x. I mean, x and y is the whatever coordinates you make it, but in the direction of like the incline, the flow is only going to be in that direction. Yeah. Or you can, it's kind of like, it's provable. So if you say du dx, that means this term goes to 0, which means that this dv dy is 0, and then you can like take this step to say that v is you're not going to have vertical velocity. But all you can really say from fully developed is that your your u velocity, or like the velocity and direction of your flow is not changing. Yeah. Yeah. So if you can prove that there is no vertical velocity, that v is equal to 0, then that goes away. Oh, also about fully developed, also the dv dx term, that will also be 0. Any velocity in the direction of your flow, all those derivatives are going to be 0. So dv dx, du dx, dw dx. In the case that x is the direction of your flow, those will all go to 0. Yeah. Yep, that's all about Navier Stokes. We can go over Buckingham Pi now. This is, I think, it's pretty basic. So the main thing about Buckingham Pi is that if you have like n is your number of variables, and then r is your dimensions. The number of dimensionless variables equal to n minus r. Cool. So, and then the 3 different dimensions you can work with are, this can be mass, length, and time. This can also be force if you want, force, length, and time. So whichever one you feel more comfortable to work with, you can just use that. So let's do a quick thing. Let's take for density. And then, also in the context of these kind of problems, kind of show what the dimensions are. Suppose you had like height. Height would be written as just L because it's just a length dimension. And then mass is just M. And any time is just easily time. Yeah. So suppose we had a let's put length here. Yeah. It's just the way you describe it. It's the way that this is written is that they're saying that mass, length, and time, or force can be written in terms of mass, length, and time, right? So if it's easier for your problem, you can just swap it out and then use force instead. It's just they're just saying is use the 3 kind of fundamental dimensions that apply to every single quantity basically. So I guess a quick quiz question. Suppose you had density. In terms of the MLT, how would you write density?
M over L cubed.
Yeah, or you can write M L to the -3, depending on what you want. So that's how you take a bunch of values and do that. The next thing is that, so now that you have your number of dimensionless variables, you need to now write them out. So the way you usually write them out is that there are repeating variables. So depending on suppose, let's say, before we do this, let's say we have an example. If you had 5 variables spanning all 3 dimensions, this would equal 2 dimensionless quantities, right? Two dimensionless quantities. And then what that means is that 5 variables, 2 dimensionless quantities, you'll have 3 repeating variables and 2 non-repeating variables. And the way that works is that you need to choose 2 variables to be non-repeating, or you basically have to choose 3 of your 5 variables to be repeating variables. Now, a lot of times, one of them is super easy because the question will ask you okay, find a function. Suppose they'll tell you to find a function of force, or some of them tell you find force as in terms of X amount of variables. So that you can automatically set that force, the thing you're trying to find in terms of other variables, as one of your non-repeating variables. And then the second one, you'll just have to either it'll be given in the problem, or you'll have to choose. Good ways to choose repeating variables. Choose repeating variables. So if you're looking at, suppose it is spanning mass, length, and time, you definitely want to make sure that within your 3 repeating variables, all of those quantities are represented. You don't want to choose 2 length quantities and 1 time quantity. That doesn't make any sense. You'd want to choose variables that look at all 3 of no, look at all three of those quantities. So represent all dimensions is your first thing. Second thing is try to choose the least complicated ones for these values. So suppose you're given like this, I don't know, viscosity, like power, length, mass, and time, let's just say, or like you're given like length, mass, and speed or something. So then use the least complicated ones to do. So don't use power as like a repeating variable. You could. It is you in this case you are allowed to use like if you as long as you follow like this requirement and you got to follow one more like can make new dimensionless quantity from repeating. So this is the second thing. Yeah. So as long as you follow these two conditions, the second one means like you can't choose like height and length as your repeating variables, because if you were to combine them, you can create H over L, which is a new dimensional quantity. So as long as you're following these two, you can basically like use whatever you want. And sometimes that won't give you like the right solution for like a problem you're trying to solve. So that's why it's like either it'll be given to you or like you have to use like you gotta like use these steps, or you can use the most simple ones. So again, suppose you're given like power, viscosity, mass, length, and like speed. So try to use mass, length, and speed as your repeating variables, because those are the most simple for you to make other quantities out of. Because viscosity is like some combination of all three, power is some combination of all three. So don't use you should use the more simple ones basically. Try to use most simple. Yeah, and I'm gonna say this is blue because it's not like a requirement, but this is kind of like a general guideline. Cool. Yeah. Yeah, if you have time, you probably won't, because like one of those will be the time scale basically. So if you have t and like w, either only use one of those in your thing. You can, I guess, either you choose which one, or they'll tell you in terms of like w or t.
So if this is like caps off something that is also
Yeah.
and to represent something
Yeah. Try to use most simple. Okay, yeah. And then the way you do this is, I'll just take another like 5 minutes on this, and we can go over like the practice question, which you will see the exact same thing. But the way you do this is that, let's say you're trying to find like A in terms of like, I don't know, rho. What else? If you have A in terms of like rho, I don't know, U, and let's say like R or height or whatever, something height. And then let's put power. This is power. Let's put force. Might be easier to go force. Okay, now we have force. What are the dimensions? The force dimensions are kilograms times meter per second squared, right? Kilogram times meter times second squared. Yeah. Oh, sorry, I thought someone raised their hand. Rho is mass times length to the -3. U is mass times time to -1, and H is just L. So the way you would do this, so right now you have what? 4 minus 3 is equal to 1. Only one dimensionless parameter. So in this case, what you would do is you would basically say that 4 minus 3 is 1. Yeah. So you would try to find some combination of these three to cancel out those terms. So right now you're trying to cancel out a 1 in your, so you're probably there's one like power of mass that you're trying to cancel out. So if you write your equation for m, you'll get there's one mass you need to cancel out plus some form. Okay, because F is gonna be this is your formula for dimensionless quantity. Something that's like what, rho to the A plus U to the B plus H to the C. Right? So basically you need to find these powers of each of these values to be able to figure out how to cancel this out. So let's start with rho. So rho has one mass term. So then based on your this like power A, you would get like multiple of these mass terms. So suppose you had like suppose A was 2, then this rho would give you an m squared term, right? So okay, actually a better way to do this. So suppose this rho would give you an m squared term. This rho would give you an m squared term. But suppose for some reason that, actually we'll go over that later. So then you would put just A here. And then for U, again, you have one M here. So you put plus B. So then this should be equal to the force over here. How much over here? So A plus B is equal to 1. Yeah. And then, yeah.
What is U?
Oh, U is, in this case, speed. Just a mass. Oh, no, sorry. Length over time. Good catch. Are we good? Otherwise, yeah, we're chilling. Okay, cool. Sorry about that. Okay.
What is H?
H is height. It's a random like length quantity, basically. So in this case, in this case, you know that A has to be 1 because that's the only term with mass in it. So for it to be able to cancel out this thing, you can only take A to the power 1. Now let's go to the second one. Let's go to mass length. Let's go to length now. So then how much, you can put an equal sign here, equal to, there's one length term over here. Okay, there's one length term. So then what do we do here? We take, let's look at rho first again. Rho, it's to the -3. So you put a -3A here, plus, what is it in U? It's 1, so you put a plus B, and then you put a plus C here for height, because it's also to the coefficient of 1. And the reason you're putting a -3 here is because every time you take rho to the power of like A's 2, that -3 exponent is going to multiply, because if you take an exponent to the power of another exponent, then those two exponents multiply, right? Suppose you had like 5 squared to like and you squared that, this is just equal to 5 to the 4th, right? So these two are getting multiplied. And the same thing here. So based on what your exponent is, it's going to multiply by this exponent. So you would have this equation for L, and then for T, you have time. So then again, equals, you're trying to cancel it out with -2. So then you'll have you just have one time quantity. So then you have -1 B. Okay. So this is pretty easy. So you know that A is already equal to 1. From this thing, you can get that B is equal to 2, because that's the only way that this time is going to cancel. This time is going to cancel out with this time. So then B is equal to 2. And then after that, you can say that you plug those two in here. You get, for L, you get what, -3, 1 plus 2 plus C is equal to 1, which is -3 plus 2 plus C is equal to 1. C has to equal to 2, right? Yeah. So then your dimensionless quantity is going to become, what's it going to be? It's going to be F over how much of each one? Only one rho. 2 rho U squared H squared. Right? So this is what it's going to look like. And this is going to equal some constant. Because if you only have one dimensionless number, then it'll just be equal to a constant. If you have more than one dimensionless number, then it's like this term is equal to a function of your other dimensionless terms, right? But for now, this is just equal to a constant. Yeah. So that's the basic way to do Buckingham Pi. The only one thing I wanted to highlight is that if you're usually they'll tell you in like all the practice and everything that you'll have a lot more than like you'll have like two different like pi terms, and if there's two different pi terms, then you write like pi 1 is equal to like f of pi 2 comma pi 3 or whatever, right? But if there's only one pi term, it's just pi 1 is equal to c, and that's how you like format your dimensionless quantity. Yeah.
So, sorry, how do we get that first equation, just the f over all the variables, and just divide it over?
That's just like a way to like write it out. So you can just use this as like how you would format your dimensionless quantity. So every single dimensionless quantity is gonna have this kind of form where, I mean, in some case, like if this row, if you get this a is like a negative number, it'll go up functionally because it's like divided by a negative exponent, which is a positive exponent. But in general, you're just trying to you're taking your non-repeating number, which is your non-repeating variable, which is your f, and you want to cancel out all the dimensions of f. And how do you do that? You just divide it by some like combination of your repeating ones to be able to get to the same dimensions, right? Okay. So you're just writing it in this form as more of like a visualization to say like, okay, we're gonna cancel out all the dimensions of f.
So I can just assume that the variables in the denominator over the force.
Yeah. So yeah, you can assume this, or this is a valid representation of it. Sometimes like the question will be like, oh, like you want to have it in terms of like this, like I think there was like a U star on like a homework, right? I think on this latest homework is like a U star, right? U star is like a function of two other variables. So you can just find it in this form and then just reconfigure it to like get whatever U star or whatever. But if you can start off from this form, you can like do the entire Buckingham Pi, get to this form, and then do everything from there. And then, yeah. Go ahead. So, yeah. So the MLT are just M just means mass, L is just length, and T is just time, right? So you already know what like in general units are for things. So force, what are the units for force? Like in metric. Like kilograms, mass, seconds. Yeah.
The way you like set up where like the F is over from, is that why your MLT is not like set to 0?
Yeah. Sorry, this is like kind of my strategy for doing it. But yeah, you can if you had everything like equal to each other, like if you had like a product, then it would be equal to 0. And that's the way that the book does it. So, and then coming back to like the other question about how you get these MLTs. So let's look at force. Force is what mass times acceleration. Acceleration is meters over second squared, right? So that's kilograms times meters times seconds times over kilogram times meter over second squared. So in the same way, we have this is basically kilogram, this is meter, and this is like 1 over second squared, right? So you're just taking whatever dimensions that are already there for the variable and just putting it, just classifying it just mass, length, or time. So if you have, let's do a quick example. If you have, what's another one? Let's do like energy. What is the equation for energy? What is, yeah, so like how would you go about trying to figure out what the dimensionless quantity for energy would be? Yeah?
Energy will be like first we have the force and then the
Yeah, so energy is, you can, from like 7a, you can say that force times distance is like work or energy, right? And you already know now, how to find force. You just do times distance. Times distance, what is distance? This is m, L, and G. L, right? So then you just multiply, you put an L squared on that. You just multiply by one more L, and then you get like energy. And how do you find power after that? Divide by T, right? Because energy divided by time is power, right? So that's just the way you just use your basic physics knowledge to kind of just like formulate those. Yeah?
So this is the thing that you would recommend like my heart for this is force.
Yeah, definitely no force, no power, no viscosity as well. Viscosity is a big thing for fluids. So definitely viscosity. I mean, obviously you can find out yourself, but if you want to just have it offhand, definitely no viscosity. Yeah?
Can you express this? Oh,
remember what it is.
And
It's Pascal's second. Pascal's second. Pascal is stress. So
Okay.
it's like I'm you can see me formulating it right now. Just I'm putting it in terms of like a bunch of stuff. So like this is the way this is my thought process. Mu, I know the dimensions are Pascal times second, and I know that Pascal is a unit of stress. So I know that Pascal is Newton over meter squared, and this is times S as well. So that I know Newton is, so this is force over L squared times T. This is a value. If you want to use F, you can just keep it like this. But now I know what F is, and I can just put it in there and then go figure out whatever mu is. Sub F. Okay, cool. That's fine. So does that make sense? Yeah?
So, like, this was solving for the first pi term.
Yeah.
But each dimensionless quantity is a pi term, correct?
Yeah, each dimensionless quantity is a pi term. That's correct. So if you, what's up?
So, like, in this case, don't we have two?
No, in this case, you only have one because you have 4 variables, right?
Oh, sorry.
Yeah, force. If you had like a fifth one, again, power, let's just say whatever. Some other, or viscosity is a very common one as well. If you had any of those other ones, then you would have 2 pi terms.
So to go to the second pi term, what would be the?
Oh yeah, so to go to the second pi term, so basically you have set, in this case, I have implicitly set that these 3 are like repeating, right? Or I've implicitly set that if I'm trying to find force in terms of these other 3, I'm saying that force is the constant one, and these 3 are all repeating. Suppose we had viscosity, you would then do the exact same thing. You would write like a mu over rho A U B H C, and you'd follow the exact same procedure, and then you would get 2 pi terms.
Okay, so the first pi term would be force, then viscosity.
Yeah, the second pi term would be, but that's as an example. You can choose. Oh god, yeah, you're gonna have to connect your thing later on.
So it's basically the terms. Okay, I get it.
Yeah. Yeah.
Another question is, sometimes in a homework it's expressed as pi 2 equals to pi and pi 1.
Yeah.
Sometimes it's pi 2 equals to pi, including all of the terms that are, I don't think, right.
Sorry, can you explain that again? What's the second thing you said?
The second one is pi, for example, like if they want to express one specific term, then we use like pi, that specific term, pi 2 equals to like phi, and then all of the other terms. It really like the final expression always be like the left hand side is the term that they want to express with, but equals to phi and so all.
Yeah, I mean, again, it doesn't matter. You can put any pi term in like the left hand side, but usually it's the pi term with the quantity that you're trying to solve for. So if you're trying to solve for force, that term would be on the left hand side.
And all of the rest will go to the other side.
Yeah. Oh, and I guess like one thing that again Arjit will be covering, but actually I don't know if he will. No, this shows up later. So suppose you have like a model, right? Suppose like you're trying to build like an aircraft or whatever. If you're trying to build an aircraft, then you have like the way that they're framing it here is that as long as you kept that dimensionless quantity the same, it'll be like the model will like a scaled model will have the same like kind of flow physics as like your larger aircraft or whatever. So suppose like you had, I mean, the most common one that people use is the Reynolds number. Reynolds number is equal to, what is it? U L or like UL over nu, I think. Yeah, something like this. So suppose you had something like this as like a pi term that you calculated. You calculated something that looks like this. If you had a model, what you would say is that U model L model nu model is equal to UL V. So in general, you're like, so the way these problems work is that you're given like your aircraft is going at X speed, your aircraft is going at like 50 meters per second. It has, it's like this big, and and like there's like this like it's flowing through air, right? And then you're like, okay, so then the question becomes like, if you have like an aircraft model, suppose the aircraft model you want it to be like 10 times smaller than your actual aircraft. How do you go about, what speed would you run that aircraft at to get the same flow physics, right? So if we were to go, like, let's just say we did that. This is like an actual problem. So it's not like a proper, like, let's say aircraft model is 10x smaller, right? If your aircraft model is 10x smaller, that means your LM over L is going to equal to 1 over 10. Or the other way is fine too. And then you're saying they're both ran through air. So if they're both in air, that means VM is going to equal, or nu m is going to be equal. This is just a different form of viscosity. This like little squiggly V I've written. So basically, you're just trying to figure out what your UM is going to be. So then you know that these two will cancel out because they're the same. And then you can then put it in terms of the other two. So you go UM is equal, UM over U is equal to L over LM. So in this case, what does that mean? So UM over U, so L over LM, this is 10. So that means that your velocity has to be 10 times the velocity of the aircraft to be able to get like technically similar physics. So in my example, I said 50 meters per second times 10 is 500 meters per second. You'll start getting into like compressible flow or some, right? Well, what is the speed of sound again for meters per second? Yeah, that's like way past like whatever. So like this is not like an actual like realistic example, but like in general, that's how you do it. You would say that UM has to equal 10 times U, just as an example. Yeah. No, this is just in my example, but if you look at it like and actually in practice, actually it's not, because in actual experiments, because they can't always scale the velocity about like 10 times, that's like really hard, or you start getting to like compressible flow physics, which is different. What they'll do is they'll use like water or something to be able to get just like different physics, to be able to still maintain that same Reynolds number or like whatever dimensionless quantity. And then they do that by switching the nu. But suppose if they told you that both of them were in air, then it wouldn't matter. Then your viscosity is the same because they're both air. But that's just an example I just used. Yeah, so definitely do not. You could memorize it if you want for like verification, but especially, I'm one of the readers, so like when we're grading on the midterm, we're going to see that you follow like the right steps. So if you just kind of like plop in with like the Reynolds number, then that's still going to be some points off. So definitely go, if it's asking you to do some dimensional stuff, go through the Buckingham Pi formula, like go through the entire thing. Like if for some reason you're like, if you're able to like tell by inspection, like, oh, I don't need to go through like this like full like algebraic equation, then you're able to like just write everything in terms of stuff and figure out like how they connect. You can like skip a little bit, but like definitely go through the Buckingham Pi formula. Yeah. Any questions on those are the three main topics? I skip anything that the GSIs or professor said in scope. Sure. Okay, cool. Prajeet, do you want to go in? What? This goes. It's not mine. Oh, we're done. Thank you. Yeah. Okay. How did I get a chart? Velocity is it's dynamic viscosity, but yeah, that's nu is like mu over rho is like what it actually is, but that's just like one way of writing the number. It's nothing you need to know, but it's just like one of the best parts. Yeah.
So one question back to potential.
Yeah.
You wrote something particularly on rate of shear strain.
Yeah.
I wrote it down, like we never talked about was.
It's just something that's in the book. It's never. I don't think it's shown up in your homeworks, but it's just like a quantity that like if for some reason you're asked about it, then like just it'll whatever equation you need will be in the book, but that's just like it's just like one of the different equations that are used to describe differential like flow, like what's happening in differential flow. It's not something that's like super important.
Also for uniform flow.
Yeah.
Have a bunch of equations for the psi.
Yeah.
In the formulation, like something.
But what does it say?
With phi is psi is u.
Oh yeah. So that's for if that's like a general if for going at like an angle, then you have to use alpha. But in case of alpha is equal to 0, it'll come out to this. So this is like it's just horizontal.
Okay.
Yeah. But yeah, so that's again that'll be given to you if you're ever asked for stuff at an angle, then you can then plug in alpha for whatever you need it to be. Yeah. Yeah, let's yeah, I'm gonna stop sharing here and I'm gonna send my the
Zoom link? Okay.
over there, yeah. I can charge you. You can use mine to like reference.
Okay.
Cool. Share screen. We have permission. You want me to hear it?
Yeah.
Cool.
Okay, cool. Everybody see that properly? Okay. So we're gonna go over a problem that kind of combines the topics that we just saw. So what it is, we have a plane Couette flow problem. It's viscous, circular Couette flow, and polar geometry. So right off the bat, looking at the problem statement, actually, there's a bunch of giveaways. Let me zoom into that actually, so you guys can see that better. I don't know. Does anyone want to like list out some of the main things that they see right off the bat? If not, we'll get to them eventually.
Can you change it to that?
Oh yeah. That better? Yeah. Okay. Cool. Sounds good. Yeah, we'll get to it. So we'll start off with the first one. Let me copy this over. So just looking at the problem right off the bat, we're going to start off by identifying the dimensional parameters that we have going on. So one of the main variables we're given is R1. So that's one of them. So we'll say that our dimensional parameters are Yep.
Read the problem first.
Yeah, sorry. Or if you guys want to take a picture or write it down, let me know. Yeah.
So make sure we have enough time to do that. You're supposed to finish it. So we did dimensionless forms.
Yeah, this one will combine both dimensionless and Navier Stokes, but in this case we have cylindrical Navier Stokes. Yeah. Okay. Good. Okay. We'll get going on this problem. So the first part asks us whether dimensional parameters that affect the wall shear stress. So that's the main thing that we're after here. And then we're asked to express their dimensions. So like we just saw, basically the units that those parameters are expressed in. So we'll start off with the first one that's just given to us, R1. I'll scroll back up here for a second. Another one that's given is R2. We're given the angular velocity of the outer ring. So that's another one. I'll write those down. So we have R1, we have R2. They gave us angular velocity. Let's see. Apart from that, they told us that it's viscous. So that's another giveaway that we're going to have that. So we can include viscosity there. That's mu. And then we have density. And the variable that we're after is the shear stress. So we have T omega, T wall. And then we can start writing out their actual dimensions. So R1 is a unit of length. So we'll give it an L. Same thing with R2, an L. Omega is an angular velocity. So we're going to have it's radians per second. So it's going to give it an inverse time. So T to the -1. Similarly with viscosity, we have mass and then length to the -3. Oops, sorry. I switched those around. That was for this one. And then for viscosity, we have mass, length to the -1, and then T to the -1. And then the last one will be another mass, length to the -1, and another T to the -1. Okay. So those are all the parameters in the problem and their dimensions. Yeah.
Where did you find the variable
Mu and rho. Yeah, so you can kind of assume them to be part of the problem parameters because the fluid is governed by viscosity, so it's a viscous problem. So viscosity is going to play a key role in the equations. And then we have some density term that is associated with your fluid. So we've got to make sure we have that included in there as well. The shear stress, yeah. I think similarly to earlier, we saw it was like units of like force over area. You could also think about it in terms of like newtons per meter squared. So typically these are the units for stress. And then you can just kind of break that down to kilograms, meters per second squared, and then we know acceleration is meters squared. Sorry, yeah. And then okay, sounds good. MLT. Yeah, you're right. You're right. Sorry. Thanks for catching that. Okay. Sounds good. All right. Moving on. So this is where we get to kind of apply the dimensionless group Buckingham Pi that we just saw. Put this down here. Cool. So looking at the dimensional parameters, we have 6 variables involved in our problem. So we have 6 dimensional parameters. And then we have 3 dimensions. So how many dimensionless groups would that end up giving you? You have 6-dimensional, 3. That's right. So we could do is k minus r equal to 6 minus 3. You have 3 where k is number of parameters, and then r is the dimensions. Okay. All right, moving on to the next part. Copy this back down. So let you guys copy that down as well. Okay. So the nice thing about this one is that they've kind of already given you what your 3 repeating variables are. So we have rho, R2, and we have the angular velocity. Does anyone want to point out why these are good, or do you have any guess as to why these ones are a good choice? Yeah.
So dimensional group is just the number of pi terms.
Yeah, let me scroll back up. Yeah. So the number of non-dimensional groups. Yeah, it's the number of pi terms. So in this case, we would have 3 pi terms. Yep. Okay. Yeah. So in this case, none of the 3 repeating variables are none of them are dependent. So we can't combine any of the 2 to give another dimensionless variable. So in this case, we can just write that none of R2 angular velocity are dependent variables. Okay, cool. Oops. I think we gotta plug this one in. I think it's about does it take a Type C, or do you have another charger?
Oh, this is all.
Okay. Yeah. Okay. Moving on to the next part. All right. So in this case, we kind of know one of them. That was just given in the problem statement itself. So they told us that pi1 is equal to TW rho R2 squared and the angular velocity squared. Okay. So now we're able to go in and pick one of the non-repeating variables and add that to get our second pi term. So one of the ones that we can go in and pick now is if we scroll back up. So we've already kind of seen this one in there. We have this one. We have this one involved. Now we don't want to pick one that's dependent. And in this case, the tau w is the one that we're looking for. So that one is the dependent variable in this case. We don't want to use that one. That leaves us with R1 and mu. So for the second pi term, if I scroll back down, we can write pi 2 is equal to R1 times R2a, angular velocity omega to the power of b, and then rho power c. And I think just another format of doing your Buckingham Pi analysis, you can say that your 3 dimensions in this case, so each of these 3 repeating variables involve all 3 dimensions. So we have mass, we have time, and we have length. So one of the ways that you can write that is you can say mass to the power of 0, L to the power of 0, time to the power of 0. And then in this case, we can just write out our dimensions for each of them. So R1 gives us an L, R2 gives us an L to the power of A, and then from angular velocity, we have T to the -1, and then for rho, we get a ml to the power of -3. And then you can combine, you can say L goes like 1 plus A times 3, and then you get a B here, and you'll get a C there. Oops. Yeah, that's right. Cool. So looking at that equations, we know that each of these have to equal to 0. So right off the bat, we know that C has to be equal to 0. So L is equal to 0. That means that in this case, T is equal to 0, so that gives us that B is equal to 0. That leaves us with the last one, 1 plus A minus 3 times C is equal to 0. And if you solve for A, you get a -1. So if C is equal to 0, B is equal to 0, and you have -1 on R2, your second pi term becomes R1 over R2. That's your second. So, okay, we'll do the same thing for the third one, R3. So we've already used R1, the one that's left. That's non-repeating and not dependent is mu. So we'll write Buckingham Pi for that one. We'll say mu is equal to R2 to the power of A. I'll go a little bit faster for this one because it's the same process. C, we can write the same formula is equal to L minus 1, even minus 1, A. I think you could have flipped them around, but you just can't use both together because if you use both together, you'll end up getting another dimensionless quantity, and that's something that you want to avoid. Yeah. So here you'll have RC. Okay, so if you set up this system, you get m to the 1 power c. You get an L to the power of -1 plus A minus 3C, and then you get a T to the power of -1 minus B. And then it just becomes a system of equations again. You know that 1 plus C must equal to 0. That tells us that C is -1. You know that -1 minus B is equal to 0. That tells you that B is -1. And the last one, you get -1 plus A minus 3C is equal to this guy. And then that'll give you A is equal to -2. So finally, you end up with your third pi term as R2 squared. What's that? And then when you're in the exam, one way to check your answer is actually if you go through the units of the numerator and the denominator, make sure everything cancels out. That means you're right. You're on the right track. You did your math right. Okay. So that basically says that this quantity depends on, these are your pi terms. R1 over R2. This is just rewriting what we just had. Okay. I'll go with that. Sorry, say that again?
Like, which part of the problem statement asks you to write?
Oh, you mean like in this format, or I mean this is just way to express your dimensional.
Look at the reduction of the last instruction.
Oh,
I guess it depends on what the problem is. If it tells you to, if it's ambiguous in the way it says, then yeah, you can write it as however you want. But if it ever tells you like, okay, write it in terms of like this, like known, like the Reynolds number, so like known dimensionless quantity, then you'll have to reformat your like parameters, like whatever variables to like do that. But if it's pretty ambiguous, then yeah, you can write it as however you want.
This part really asks us to write this.
Yeah, this is just like a random practice problem. So this is not like yeah, so this is not like what the actual like if the exam tells you to be ambiguous with it or it doesn't say anything, then you can write as much as you want. But this is like a random problem. So I wouldn't like necessarily count on the fact that it'll be like exactly like this on the actual exam.
cool. Okay. Moving on to, so this is a Navier Stokes problem. We're looking at it in cylindrical coordinates in this time, so not in the standard Cartesian coordinates. If we scroll back up, the question asks us, what are the boundary conditions on u theta and u r? Okay, so if that's your problem setup, let me also bring this down here. Sorry for all the scrolling back and forth. Okay, so one of the boundary conditions right at R1. So R1 is a fixed boundary, so we know that right at the boundary, we have a no slip condition. No slip, which means that in the theta direction, R is equal to R1. Sorry, U theta, R is equal to R1. Your theta direction velocity is equal to 0. And then similarly, at the top, same condition. R is equal to R2. Sorry, not the same condition. This is where your angular velocity comes into play. So if you have no slip at the top surface, what does your theta direction velocity end up being if there's no slip? R, yeah, exactly. Essentially, you have the same velocity at that point. So it's just your angular velocity times R. Yep. We'll have two more boundary conditions. We'll have no normal flow. No normal flow. Yeah. R2 omega. 2 omega. So I think, yeah, actually you're right. Sorry. You're right. That should have been R2 omega because you're at R2 at that point. Good catch. Thank you. Okay. For our no normal flow boundary condition, we'll start with the bottom boundary at R1. So normal flow is given by your radial velocity UR, and when we're at R is equal to R1, that has to be 0 because we don't have flow going through the boundary. And then if we're at the top boundary, UR would be 0 at R2. So, why both of you did it?
Yeah.
Okay, so this is the solid boundary, and this is the solid boundary, right? So if you're at a solid boundary and your flow, I guess, penetrates into the wall.
Or more like each sentence in the question, sorry, the question state prompt statement tells you that there's no R direction.
Okay, so in that case, we're given that it's a wall. And usually when you have a wall condition, that's something that you would, that you can assume. But there's going to be no normal velocity into or out of the wall, essentially. So any velocity in this direction has to be zero.
Into the.
Yeah, like into the actual circle. And then similarly at this boundary, it's again a wall. So you don't have any velocity, I guess, jumping out of the actual solid boundary. So essentially your radial velocity is equal to zero at both boundaries. Does that make sense?
So which part of the Bible is the wall?
Oh, sorry. So this right here is your wall, and then the same thing back out here. Sorry, I should have known what to do with that. Yeah. So you have two cylinders essentially, your inner cylinder, outer cylinder, and your fluid is trapped within the two regions.
Oh,
The two cylinders.
oh.
Yeah, so that way you can assume that at R1 you have a wall and R2 you have a wall. Sorry, I should have been a little more clear with that. Okay. Let's move on to the next part. Okay, so we have our boundary conditions. We will be needing those later. Now we'll start thinking about assumptions that we can make about the problem. So before I scroll back down, so this is what I mentioned about making sure you read the problem thoroughly. There's a bunch of assumptions that we can make just reading the problem statement. One of them being that the flow is steady. So what does that mean if your flow is steady? Yeah, that your du dt term ends up going to zero. Can anyone spot another one? Yep, yeah, that's one of them. 2D. What is alpha? Yeah, exactly. No change data. So let's go ahead and write those down. What assumptions can we make? So the problem statement tells us that we're steady. That means that du dt is equal to zero. We're 2D, which means that theta dc is equal to zero. Similarly, u is equal to zero. And they also told us that we're axisymmetric. Okay, I'll try to pick up the pace since we're running out of time. So now that we have these simplifications, we can start crossing out terms from our Navier Stokes equations, and that'll simplify our lives a lot more. Okay, so looking at just continuity, we know that u theta, because we're axisymmetric, there's no change with theta, so that goes to zero. Let's see. Actually, okay, let me come back to that. Let's start with the next part of the problem, and then we'll make our simplifications, because we're going to need a part from continuity to do the rest. So we'll start from continuity. Okay. So continuity is that first equation that's given to us right at the top. This guy. And then we know that we're axisymmetric, so that term can go to zero. Okay, so now we have an equation for UR, since we're looking for the radial velocity. Looking at that, I can cross out the R term because the other side is just zero, and that leaves me with this derivative. I can integrate both sides. That'll get rid of the derivative term and give me constant that I can call C. And then we can solve for UR just like that. where C is our constant of integration. And then from the boundary conditions that we found earlier, we know that the boundary condition, yep. So basically, when you take the integral of 0, you just set it to a constant. Basically, like if you think about it the other way around, if you take the derivative of a constant, you get 0. So oh, where does the RUR? So that's just coming from cylindrical Navier Stokes. So when you let's see, integral of that. I guess, let's see, I can specify that we're integrating with respect to R. So basically you're taking the integral of a derivative, and then what you end up with is just what's inside the actual derivative. So that's just you isolate that. Yeah. Yep. So boundary conditions, I bet that'll give you UR at R is equal to R1 is equal to 0. That gives you a C1 over C over R1 is equal to 0. So that way we know that C has to be equal to 0. That also tells us that if C is equal to 0, UR is equal to 0 everywhere. So the radial velocity component all along the two cylinders has to equal to 0. Okay. We'll move on to the last part. We're getting there slowly. Okay, so we did our continuity. And then let's take a look at the last part. Okay, so now that we have our assumptions made, we can start looking at the theta component of Navier Stokes. So this is just part of the problem statement. They told us that they want us to look at the theta component of Navier Stokes and use your boundary conditions to find an equation for the tangential velocity. So, but before I do that, I can start looking at each of the terms and crossing things out because I know certain things. So we know that steady, so the time derivative has to be equal to 0. We found that UR is equal to 0 everywhere, so that can go to 0. We know that we're axisymmetric, so there's no change in the theta direction. That goes to 0. Again, we found that UR is equal to 0. And something that they told us in the problem statement is that the pressure can be assumed to 0. We can neglect that. And then finally, there's the last couple terms right here that can go to 0. So if we write that out, the other side goes to 0. R 1 over R. Oops. Sorry, which part? For the P, so that's part of the problem statement. I say that assuming that P theta, dP theta is equal to 0. Yeah. I'll just write out the rest of it so we can integrate once. 1 over R. C1. And then you can integrate again. Okay. So now we have our equations in terms of C1 and C2. And then to be able to solve those constants, we're now going to apply the boundary conditions that we had earlier. So we're going to go back to our boundary conditions. We can say apply your boundary conditions at R is equal to R1. We know that U to R1 is equal to 0. So that'll tell us that C1 over, sorry, that's a 1. C2, that'll tell us that C1 over 2 is equal to C2 over R1 squared. And then we'll apply the next boundary condition. Yeah, so this is the boundary condition at the second interface. So now we have an angular velocity at the top. So we can't just say that this one is going to be 0. We get the right omega R2 for this boundary condition. And then we can write, let's see. Yep, so just continuing on with that. Now we know that C1 over 2, C2 RT squared equal to this. That'll give you a C2. And then I'm going to solve everything in terms of C2. And then that'll also give me C1 from the other boundary conditions that the other equations that we had from our boundary conditions. Okay, so now we have our C1, we have our C2. We can plug back into our expression for U theta. This guy right here, I'll bring that back down. Duplicate that. So U theta is equal to sorry, a little bit sloppy. So at this point of the problem, it's mainly just algebra and rearranging terms. And that will be your U theta. Okay. Yep. Yeah. UR will be 0 everywhere. Okay, sounds good.